Last semester we had learned this theorem that if x and y are two independent random variables, both of which are simple, then expected value of xy equals expected value of x times expected value of y. Now this result, which proved quite useful last semester, actually is far more general than merely for simple random variables. But since once we drop this simple condition, now expectation may be infinite or may even be undefined, we may have problem with one or both sides of this equality. So we shall put some extra assumption. The condition is that expected value of x and expected value of y are both finite, then we have the same consequence. Observe that I have not assumed existence of expected value of xy. That is actually also part of the implication. So writing more explicitly, we should say expected value of xy must be finite and then our usual equality. Now this result is actually general, but we shall prove it only for random variables that have densities. So we shall assume in our proof that they have got densities fx and fy. So fx is the density of x and fy is the density of y. Because I have assumed independence, I also have joint density of xy, which will be this times that. In order to prove this result, we shall need one little fact from last semester, that for any random variable z, expected value of z is finite if and only if expected value of absolute z is finite. The advantage of using this condition is that this being a non-negative random variable, this expectation must exist, though may be infinite. But this expectation is more troublesome. It could be infinite, finite, and also may not exist. So that is why it is easier to work with this condition. In order to show that this must be finite, what we shall show is expected value of absolute xy is finite. Now expected value of this being non-negative, here I can use that integral formula where this is the joint density of xy. Now because I know that x and y are independent, so I know that the joint density exists and is equal to fxx times fyy. So this integral becomes integral of mod xy times fxx times fyy. Now you see the integrand nicely factorizes into things which involve x only and things which involve y only. So you can just put all the x things together and the y things together to get an integral in terms of x only times an integral in terms of y only. And this we immediately recognize as expectation of mod x, and similarly this is expectation of mod y. So this is equal to this times this. I am told that both these things are finite. Remember, I was told expected value of x is finite, which I know if and only if expected value of mod x is finite. Similarly, this is also finite. Product of two finite things is finite, so this is finite. And I have shown that expected value of mod xy is finite. Hence, expected value of xy is also finite as required. Now, since I know that this is finite, I can use the integral formula for expected value of xy. Again, exactly the same argument, except that I shall drop the absolute value notations. So once I drop the absolute value sign, I will also drop the absolute value signs from here, and also from here, and also from here. As a result, I will get my desired result, that expected value of x times expected value of y. And that completes the proof of the theorem. Two points are in order here. Suppose I have x and y jointly distributed with finite expectations. Then we saw just now that if x and y are independent, then we have this. But you must remember, we do not have the opposite implication. Even if x, y are jointly distributed with finite expectation of x, finite expectation of y, and this is also finite and this equality holds, still x and y need not be independent. We had already seen counterexamples of this when we worked with discrete random variables, and the situation is not going to mend even when they have got joint density. We are going to see a counterexample in the exercise. The second point is that when we said xy independent, we also got this conclusion that expected value of xy is finite. This was part of the implication, not part of the assumption. We just assume these two things are finite. We got that this is also finite, and we got this. Now sometimes students have the wrong idea that if I forget about this condition, then, well, I understand this condition may break down, but anyway, this condition will always be true. So even if I give you any two jointly distributed random variables with finite expectations, even if they are not independent, still expectation of xy will be finite. That is not true. It is possible to have xy jointly distributed with finite expected value of x and finite expected value of y, but this is not finite. It could be infinite, it could even fail to exist. The exercises in the class web page will give you counterexamples for that, and you may try your brain just to see if you can come up with your own counterexamples. In this exercise, we start with x having density fx equals half from -1 to +1, 0 otherwise. In other words, it is uniform over the interval -1 to 1. And I take y equal to x squared, then clearly x and y cannot be independent. Y is completely determined by x. Now the question is, you have to find expected value of x, expected value of y, and expected value of xy. And after that, you have to show that expected value of xy equals expected value of x times expected value of y. Thus, we find that this equality holds, yet x and y are not independent.